Hello everyone. I'm Takuji Yamada from Institute of Science Tokyo. This time, I explain about the microbiome spectra and the prevalent Corybacterium-associated mutational processes in Japanese colorectal cancer. And this is already published in preprint, so please check this the DOI. And then for the background and then unmet needs for the early onset CRC. So early onset CRC is younger rather than 50 years old is rising globally since the 1990s. So Japan also shows especially high burden. So this is reported in this year, and this is colorectal cancer across 11 countries. Percentage of the early onset also are reported. In Japan, it's quite higher compared with the other countries. So this is a high, strong issues in Japan as well. And then, so the gut microbiota, I always focusing on the gut microbiota, gut microbiota, and gut microbiota and the colorectal cancer associations, and then that is also implemented. So PKS plus Corybactin produced E. coli, and then endotoxical Bacteroides flagellus, and another Fusobacterium nucleatum, Peptostreptococcus tomatis, and the Paludinomas micro, and those kind of things, those kind of bacteria are also reported strongly associated with colorectal cancers. But however, the patient level prevalent timing of the mutational process and the immunocontext has been still unclear. And then that's why we design our study and a cohort. So the observational cohort at National Cancer Center in Japan and Tokyo, that is from 2040 and 2070. And the number of the CRC patient, colorectal cancer patient, is 138, and then plus healthy control is 146, and then screened by the colonoscopy. And then we also not only for not only for gut microbiota, but also we also check the genomes sequences for the same host. So this integrated design let us aligns two microbial features with tumor genomes, tumor genomics. And along those lines, we do that kind of firstly, we make a crash fire together with explainable AI and then subtype of colorectal cancer based on the microbiome. And a random forest crash fire trained on the 4 external cohorts firstly. Then we applied sharp value they computed per patient, and they applied the PCA and the k-means and the full microbiome-based subtypes we did. So this is a whole overview of the workflow. And firstly, we train crash fire compared with the healthy control and microbiome patient, cancer patients. And then after we constructed the crash fire, we using this crash fire, we applied our CRC patient and healthy control, and then apply the explainer based on SHAP values. And then after we get the SHAP value, we do the PC analysis based on the SHAP value, and then do the k-mean clustering, and then CRC crash fire of this that we did. And based on the crash fire and the explainable AI, we clearly show the 4 subtypes, even for the cancer patients, and based on the microbiome analysis, it's very clear 4 types from the CRC patients. And for each patient, have a specific microbiome patterns, and sorry. So Peptostreptococcus tomatis of Fusobacterium nucleatum are higher contributors for this crash fire, and then but this is totally depending on the cluster. For example, this is subtype 2, and then subtype 2 strongly have a Fusobacterium nucleatum and the Peptostreptococcus tomatis are overrepresented compared with the others. The other subtypes are not the kind of these cases. And then Fusobacterium, so this is also this gradation in a PCA plot represents the predicted CRC probability, and then so subtype 2 have a higher probability compared with the others. So even the CRC patients, they have a tons of diversity based on the microbiome patients. And then, based on this subtyping, we do the clinical and the prognostic differences by subtypes. So the age or tumor microbial load and the prognosis. So interestingly, we have a we did a Kaplan-Meier curve for each subtypes, even for the discovery cohort and the validation cohort as well. And then in a discovery cohort, it's a totally different the survival rate based on the subtypes. And this tendency is the same as a discovery cohort and the validation cohort. And then this is the detail kind of the heat map of metadata for each subtypes, the age, sex, body mass index, and the stage of those kind of things, together with the alternation mutation patterns based on the genomics, tumor genomics. And then this is microbiome patterns. So this is a subtype. Check the subtype 2 and subtype 3, and then there are tons of differences compared with the another subtypes. So and then okay. So this is also the another interesting cases. So Coribactin mutational signature that are also prevalent. So SBS88 or in the ID1D is called as a mutational signature. It's kind of the mutational signature is kind of the patterns or the mutation patterns for the cancer progressions. So and each mutational patterns are categorized to the something like oncocausations patterns. For example, SBS88 on ID80 A10 is associated Coribactin mutation patterns. So in Japan, in our data, sorry, so we can see in our data, more than 90% CRC patients have this ID8 or SBS88 mutation patterns, and even the higher contributions is over less than 40 years old, and in the subtype 3. And then I will go to here. So this is one of the mutational pattern, the hotspot in the APC mutations. So SBS88 and the ID18 are they have a hotspot in close to the APC genes mutation, which are one first mutations, the causation mutations for the colorectal cancer. And then, so here is the data for the upper parts is the average of the proportions of the SBS 88 and the ID 80 in Japanese cohort. And this is 138 peoples, and this is the percentage. So more than 90% of the patients have this patterns. It's strongly correlated to their early onset cancers. And then the another things that is a proportion of SBS 88 and the proportion of ID 80 are strongly associated with the average of the proportion of the adenine 3,4 base upstream of in APC mutations. So this is strongly associated SBS 80 even in our cohort data. This is the same as the previously reported data, reported result. And then, so this is the other interesting cases. So this is timing early clonal events and age relations. So that is a bit difficult to calculate the estimation of when the mutation happens based on the genomic data, and then we estimate when the mutation happens. And interestingly, Coribactin signature enriched among early clonal mutations compared with the late or subclonal data. So this is a kind of the data. So this is the upper one is early clonal data. So just a second. Yeah. So the percentage of SBS signatures examined in both early and late clonal genomic abnormalities, and the patient with higher percentage of the SBS are displayed in top row, organized from left to right. So and then here, so in the parts, in the upper part, so the patient with higher percentage of SBS are displayed in the top row, and then the organizer to left to that. So, so here's the another things. uh, and then, so in the top 30 cases for the left data, we can say that the Corybacterium mutation is the top 30 cases, they are estimated, and then in early time, it's more than age, it's less than the 40 or 30 and 20, they have a high mutation rate in the early of our life. Sorry, that's so. This is the conclusion. The four microbiome-based CRC subtypes with distinct clinical properties and Corybacter mutagenesis is prevalent in Japanese cohort, even in early and inherited young patients. And then implications for this data is a modifiable risk the diet microbiome interventions to reduce Corybacter. We are not sure yet. The early detection integrates tool markers with genomic signatures. And then this is short time, but I'm very welcome to discuss. And then this is acknowledgement for both of the researchers. Thank you very much.